Hi, this is Dr. Habib Ahmad, and today I'm going to show you how to perform the Silvaco TCAD simulation of concentrator solar cell. Concentrator photovoltaics, also known as CPV, focuses sunlight onto a smaller area of a solar cell by using either a combination of mirrors, as you can see in this configuration over here, or by using lenses. Now, by focusing sunlight onto a small area, less photovoltaic material is required. Photovoltaic materials become more efficient as the light becomes more concentrating. So, the highest overall efficiencies are obtained with concentrating photovoltaic cells and modules. However, for this purpose, we have to use more expensive materials, manufacturing techniques, and also we have to track the movement of the sun. So demonstrating the necessary cost advantage over today's high volume silicon modules has become more challenging. A concentrator photovoltaic system comprises of a solar concentrator with mirrors or with lenses, a tracking mechanism, solar cells, and a heat sink. Because since we are actually focusing light onto a smaller area, so it's going to generate a high amount of heat as well, and in order to take away that heat from the devices, we need to use big heat sinks for that purpose. So unlike the flat plate photovoltaic systems seen on the roofs, solar concentrators must track the sun to focus the light onto a solar cell throughout the day. And sun tracking increases the daily energy production above that of non-tracking photovoltaic panels. However, electrical output drops dramatically if the sun is not focused on the cell or if clouds block the sun. So here are the two configurations. One of them is using mirrors in order to focus the sunlight onto the solar cell, and the other one is using a lens in order to focus the sunlight onto the solar cell over here. Talking about the lenses, mostly Fresnel lens is used for focusing the sunlight onto the solar cell, which is a type of composite compact lens which reduces the amount of material required compared to a conventional lens by dividing the lens into a set of concentric annular sections, as you can see over here. So this way we can reduce the area of the lens. And then you can see the sunlight is going to strike this lens. This Fresnel lens focuses light onto a smaller area solar cell. Let me show you a couple of actual examples of the installation of these two kind of configurations of concentrator solar cells. So here you see several 35 kilowatts concentrator photovoltaic systems built in California and installed in Arizona, and the system actually uses Fresnel lenses to concentrate sunlight onto high efficiency silicon solar cells. And you see the pickup trucks over here in the shade. It actually gives the idea of the size of this installation. So these are like huge. Also, here is another practical example of the installation of concentrator photovoltaics. So these are actually several 25 kilowatts concentrator photovoltaic systems built in Australia, and these systems actually use mirrors for concentrating the sunlight onto silicon solar cells. And you see the people over here, like in the foreground. It gives you an idea of the system's size. So even these systems are like huge. but actually they concentrate sunlight onto a smaller area solar cell by like hundreds of times. Here is an example of an actual of the efficiency of an actual solar cell. So it is a monocrystalline silicon solar cell having an efficiency of approximately 21% at 1 sun under the AM 1.5 spectral conditions, which correspond to 1 kilowatt per meter square, or you can say 100 milliwatts per centimeter square. However, as you can see that the efficiency of this solar cell increases to approximately 500 to approximately 26.5% under 500 suns. So concentrator solar cell actually increases the efficiency of the solar cells by a big number. And further increases, however, in the solar cell concentrating requires careful packaging of the designs, because it's going to result in more amount of heating. So with further increase above 500 suns, there will be a decline in the efficiency, as you can see over here in this plot. Now, with that preliminary information, let's start talking about our code. So initially I'm going to show you how to perform the Silvaco TCAD simulation of a silicon PIN solar cell under 1 sun, and once I run the simulation for that structure, later I'm going to show you how to perform the Silvaco TCAD simulation of the same structure under for concentrator solar cells. So in this example, here is the meshing. My structure is running from 0 to 10 micrometers in the x direction and from 0 to 20 micrometers in the y direction. My material is silicon. The top electrode is anode, the bottom electrode is cathode. I saved the structure, and then I call the structure in another block of Atlas. Here for the entire structure, I define an initial doping of 1 into 10 to the power of 14 per centimeter cube, and then I define Gaussian distribution doping of 5 into 10 to the power of 18 per centimeter cube, p-type at the top, and 5 10 to the power of 18 per centimeter cube n-type at the bottom. This parameter over here is related to the Gaussian distribution of ion implantation of doping. Here I have defined some material parameters, the electron and hole recombination lifetime, and by using this command I'm actually calling the optical properties of silicon. As you know that silicon used here in this structure as a solar cell is going to have some refraction coefficients, refractive index, and it's also going to have some absorption coefficients, and these parameters vary versus wavelength. So Sopra is the command to call those files into our Silvaco TCAD code. Then I'm introducing some models. Then a method is required for calculating the solutions to semiconductor devices. Then I use the command of output to look at certain parameters, for example optical intensity, energy band diagrams, electrons, holes, mobility, and some other stuff. Then I want to save the structure here with this name, and then with this command we can plot the structure. Here in this block of code I am creating a log file of Habib_dark, and then I run a sweep from 0 to 0.6 volts for anode in order to look at the IV characteristics of this structure under dark conditions. Then I want to look at the IV characteristics of this structure under light conditions as well, and for that purpose the first step in the solar cell analysis is to illuminate the device, and we can turn on the illumination by assigning the beam intensity on a sol statement. Like over here you can see the sol statement, and here we define the beam intensity. However, in some cases we may encounter convergence difficulties, and we may need to ramp the light intensity from a lower value to 1 kilowatt per meter square. So like here I have assigned it a value of 1, which represents 1 sun corresponding to 1 kilowatt per meter square, or you can say 1000 watt per meter square. But we have to ramp it up from a lower value in order to avoid convergence issues. So I start with 1 watt per meter square to 10 watts per meter square to 100 watts per meter square to 1000 watts per meter square, or you can say 1 kilowatt per meter square, or you can also translate it to 100 milliwatts per centimeter square. Then I create a log file with this name in order to look at the IV characteristics of the solar cell under light conditions, and I run a sweep from 0 to 0.6 volts. With this command I overlay the IV characteristics under dark and light conditions, and then I save the structure under light conditions and plot the structure. Here are the commands for calling the log file under light conditions, and then to calculate the short circuit current density, open circuit voltage, maximum power, fill factor, and efficiency. I already discussed it multiple times in the previous videos, so I'm not going to go over those details time and time again. In this block of code, I want to look at the spectral response of the silicon PIN solar cell. So I want to see the spectral response in the range of 0.3 to 1.2 micrometers, and then using this block of code I'm actually calculating the internal and external quantum efficiency, and then I plot the internal and external quantum efficiencies in the same figure. So now let us run the code. It's gonna take some time. Here is my solar cell structure under thermal equilibrium. So if I go to display in meshing, before meshing I want to show you the anode and cathode. So this is my anode, this is my cathode. Then we can also see the meshing. So as you can see that the meshing is denser at the top and also over here at the bottom, but it's sparser in the middle. And the reason I've kept it denser at the top and also at the bottom is because if I click on contours and then go to define and then contours, click on absolute net doping, so from this structure you can see that here is my structure, and for some reason I don't know why it's showing it's actually simulated until 20 micrometers. So it should have been simulated until, okay, so there is a problem with this one. Let me stop this simulation and let me run it once again. After making the correction, so I wanted to make a structure from 0 to 10 micrometers, and for that purpose let me quickly make the correction. Alright, so that is fine. And then what else? Talking about the dopings, they are fine. Let me check the anode and cathode. So everything else is fine. So let me run the simulation once again. Apologies for the delay because of that minor mistake. I was working on different structures, and when you are working on different structures, sometimes you mess up things. So now you can see the meshing, and I want to see the dopings. So here we go to contours, absolute net doping. I want to see that, so click on apply. So now we can see that we have a high doping over here at the top and also high doping over here at the bottom. Basically we have Gaussian doping at the top surface and also over here close to the bottom. We have, and we can also click and see the anode and cathode contacts. So we can see that as well. We have the anode over here and the cathode over here. We have p-type doping at the top and n-type doping over here at the bottom of the structure. You can also see the doping levels by introducing a cut line in the structure. So here is the doping, close to 510 to the power of 18 per centimeter cube at both ends, but it's 10 to the power of 14 per centimeter cube in the middle. And similarly you can also see the energy band diagram of this structure by clicking on these options. So here is the energy band diagram of this PIN structure. We have a p-type layer over here. That is obvious from the fact that the Fermi energy level is close to the valence band here on the left side and is close to the conduction band on the right side. So it means that we have n-type doping over here. The structure is already simulated. From this structure we can see the IV characteristics under dark and light conditions. So the green curve represents the IV characteristic under light conditions, the red curve under dark conditions. Similarly, we can also see the power curve, and we have the maximum power point around here. Similarly, we can also see the spectral response range of this silicon PIN solar cell. Here is the spectral response range of this structure. Similarly, we can also see the internal and external quantum efficiencies. So as we can see that the external quantum efficiencies are lower as compared to the internal quantum efficiencies. This blue trace over here also takes into account the losses due to incomplete absorption. But I'm more interested in looking at the figures of merit. Before that, we can also see the photogeneration rate and the photon absorption rate. Let me look at the photon absorption rate. So I click on apply, and then we can draw a cut line across the structure as well. You can see that the photon absorption rate is exponentially decreasing across the structure. Our light is incident over here at the top, like across around 5 micrometer in the x direction. Its absorption rate is decreasing exponentially as we further go down the structure. Now I'm more interested in looking at the figures of merit. So here is my short circuit current density, open circuit voltage. The fill factor is around 75, which is not bad, and my efficiency is 17%. So let me record those values in a snipping tool. Let us keep it to the side. Now what I want to do is I want to see the simulation of this structure under 2 suns, so which would make it a concentrator solar cell. So for that purpose, the procedure is really simple and straightforward. Let me close the previous figures before that. So I go to this section of the code, and here, as I already told you, that we ramp the intensity from 1 watt per meter square to 10 watts to 100 watts and finally to 1 sun, which corresponds to 1 kilowatt per meter square. Now for 2 suns, what we do is we introduce this line, sol B1 is equal to 2, which makes it a concentrated solar cell. So it's that simple. For 10 suns, you just have to write sol B1 is equal to 10. For 100, you write sol B1 is equal to 100. So it's going to focus light that many times. So in this case, our light is concentrated onto the solar panel by 2 times, which means that the intensity of light on our solar cell is now 2 times, or you can say 2000 watts per meter square. So that's the only change we are going to make into this code, and now we are going to run the code to see the results. It has already gone past the IV characteristics of the solar cell under dark conditions. The structure is illuminated with 2000 watts per meter square, and now it's running a sweep for the IV characteristic under light conditions. That part is also done. Performing some more simulations now. Now it's simulating the spectral response part of the code. Okay, here are the IV characteristics now, and then here is the power curve. And I'm more interested in looking at the figures of merit, so I directly jump to that part, and I want to compare it with the figures of merit under 1 sun condition. So here you can perform that direct comparison. So as you can see, for the concentrator solar cell, when the light is focused 2 times, now my current density is 87.25 milliamps per centimeter square, while under 1 sun it was 43.6. So it has almost doubled. Similarly, my open circuit voltage has slightly increased from 0.52 to 0.54, which is according to the theory of solar cells. If we increase the short circuit current density is directly proportional to the input light intensity, while the open circuit voltage increases but by a really small number. If you go to my solar cell video, the video on solar cells, it's a theoretical lecture. I've discussed in detail why the open circuit voltage only slightly increases, but the short circuit current density is directly proportional to the input light intensity. Similarly, the fill factor now has slightly increased as well, and the efficiency has increased from 17 to 36%, which is a big increase. So we see that in case of concentrator solar cells, these parameters improve, especially the short circuit current density and also the efficiency. The efficiency also almost doubles because the efficiency is proportional to the current density of the solar cell. Now we see that the short circuit current density almost doubles. If we double the intensity, it's going to increase further. If we further increase the light intensity, like under 5 suns, it's going to be even higher. Under 10 suns, it's going to give like even a higher value. In actual concentrator solar cells, if you concentrate the light by 100 times or by 200 times, by 500 times, this heats up the device as well, and because of that heating up, we don't actually achieve the theoretical performance of the device. We have to take away the heat. We have to cool down the solar cell in order to have a reasonable efficiency. So in actual setup, we don't really get these high numbers, like especially for a light intensity which is 2 times the AM 1.5 conditions, but still this simulation gives us a good idea into concentrator photovoltaics. I hope this session was useful for you. Take care until next time, and I will talk to you next time. Take care. Bye. Adios.